Chapter 9, Alkynes. In this chapter, we will learn the behavior of alkynes in terms of acidity when it's reacting with bases. We will learn how to name alkynes and how to prepare them from other function groups. And we will discuss reactions of alkynes and how similar they are to some of the reactions that we have seen already in the alkene chapter. Now, alkynes usually have the formula of CnH2n minus 2. So it costs the alkane 4 hydrogens to lose to make an alkyne single unit. And that single unit of alkyne usually has an IHD of 2. So every single time you have an IHD of 2 and you have an alkane or a hydrocarbon chemical formula, there might be a chance that you have an alkyne unit. Some reactions, as we said, similar to the alkene reactions, such as addition and oxidation, and some of these reactions are just specific to alkynes. So we will see that in the second part of this chapter. IUPAC. Now, just like any other functional group, we always have to find the longest chain of carbons, and that longest chain of carbons in the case of alkynes has to be part of it. So once we find that longest chain of carbons, where the alkyne is part of, we number the chain from the side that's closer to the alkyne unit. And the alkane will sound as alkyne. So A and E will be replaced with Y and E. So let's take examples. So here is one. So we can see here there's 1, 2, 3, 4. So 4 carbon chain. And I have to start from the carbon on the left, as it is the first carbon in the chain carrying the alkyne. So what do I have? I have 4 carbon chains, so that's a butene, and I have to indicate where the position of the alkyne unit, then that's the locant. So the locant has to be part of the parent name. So instead of saying 1-butene, which is also acceptable, but the new set of rules set by IUPAC, it forces us actually to have the locant within the parent name. So but1-ine would be the proper name for this structure. Here's an example of a terminal alkyne. When we say terminal alkyne, that means the alkyne unit is at the end of the chain or the beginning of the chain. So that's basically giving you the alkyne to be on carbon number 1. When I say internal alkyne, that means the alkyne unit is within the longest chain of carbons. It's not at the terminal. So here is another example. So we have 4 carbon chain and the alkyne is on carbon number 2. So that's a but2-ine, but2-ine. We will see soon how in base reactions with alkynes, that the terminal one will be the one that's going to react, not the internal, and we will see why that is. Now, this is important to mention. All other functional groups, except ethers and halides, have higher priority than alkynes. What is that supposed to mean? If I have an alcohol in the chain, then the numbering will be closer to the alcohol group. If I have an alkene in the chain, then the numbering will be closer to the alkene. If I have a ketone, if I have an aldehyde, if I have a carboxylic acid, they all going to have a higher priority when numbering the chain, as they will be the parent name of the compound. The alkyne becomes a substituent in that case. Except if I have an ether or I have a halide, then the alkyne will be the one with higher priority. So this is some examples of common names you are free to use, but if the question is asking you for IUPAC set of rules or IUPAC name, you have to follow the rules discussed previously. So here is basically an example of a terminal alkyne again, 1, 2, 3. So that's a propyne or prop1-ine, prop1-ine. Here's another. So you have 1, 2, 3, 4, 5, 6, 7. So you have a 7 carbon chain. And you have 2 methyl groups, one on carbon number 2 and one on carbon number 6. So that's a 2,6-dimethyl hept3-ine. 2,6-dimethyl hept3-ine. So that indicates that the alkyne unit is on carbon number 3. Thermophysical properties, usually hydrocarbons are nonpolar due to the fact that they form London dispersion forces. Water forms hydrogen bonding, so that's that difference in between those molecules in terms of intermolecular forces make them immiscible, and that's why alkynes usually are soluble in organic solvents, in a lot of organic solvents, actually, examples. Boiling points are comparable when we compare them to a similar number of carbons of corresponding alkane. They may be a little higher, so some of these alkynes may have some higher polarity than other hydrocarbons, so you may find that, but in general, they have comparable boiling point. They're less dense than water, and when on up to 4 carbons, usually they are actually gaseous compounds at room temp. This is ethine. So ethine, the common name for it is acetylene. It's used actually in welding, and as it's the oxyacetylene flame reaches temperature as high as 2800 Celsius. So that's useful. And we've seen that the hydrogenation actually, it gives releases 234. So when it decomposes down to its elements, you could see here actually that the energy being released, it tells you that the compound, which is the alkyne, it's thermodynamically unstable. So that's compared to alkene or to alkane. Alkane would be the most stable in terms of decomposition. Here's the experiment of basically using acetylene in welding. So you will basically start with an anthracite coal with lime, and heating it up, it will form calcium carbide. Throwing water on calcium carbide will release acetylene plus calcium hydroxide. That's an experiment they usually used industrially. We don't do it in lab for the purpose of releasing acetylene, obviously. Here's another way how to make acetylene from natural gas. So that's using 2 molecules of methane, high temperature, 1500 Celsius. It's a very quick process to give you basically an acetylene structure. So this is another industrial application where you basically generate acetylene, whether you're coming from anthracite coal through the carbide or the natural gas source. In terms of structure, alkynes, they have a triple bond that's formed. Usually it does have the sigma bond and 2 pi bonds. The sigma bond usually have the sp orbitals overlapping to form that sigma bond, and the pi bond, since we have 2 of them, each one is going to require 2 p orbitals to overlap. So we have a total of 4 p orbitals to form the 2 pi bonds that we have in the alkyne. The shape of the molecule is usually linear, so that's why the bond angle is about 180 degree, and that becomes important that when we draw the alkyne, we never draw it in a zigzag formula. So we make sure that the alkyne unit and whatever attached to it, it's going to be in a 180 degree bond angle. So you could see here example. So this bond and that bond has to be actually 180 degree to the alkyne. So that's how we usually draw the alkyne structure. In terms of bond length, the triple bond usually is the shortest when we compare it to an alkene or to an alkane. And that's been proven with numbers as well. So we could see here the 1.54 angstrom compared to 1.2 angstrom for the alkyne. And not only that, the hydrogen attached to the alkyne, you could see slightly smaller bond or shorter bond compared to the C single bond CH bond. So 1.06, 1.09. And the reason behind that is when you have more S character carbon, the shared electrons becomes closer to the nucleus of that carbon, and that will basically bring the hydrogen closer, but not that much. I mean, you could see here clearly that the difference is not much. But when you talk about triple bond versus double bond versus single bond, you could see clearly there is a difference between those bond lengths, and that affects acidity. So when I have the pKa chart, I will find the following: that the alkane pKa value is about 50. Alkene is about 44. And we're talking about the hydrogen attached to the alkene. Hydrogen attached to that C single bond C. Hydrogen attached to the alkyne unit is about 25. Passing by the nitrogen, hydrogen, we'll see it, it's about 33, 36. Alcohol is about 16 to 20 pKa, depending on what R group is. So we could see clearly that the alkyne hydrogen is, in terms of acidity, it falls in between OH and NH. So that's important to explain why that is. And the reason behind it is the hybridization type of the carbon that's the hydrogen attached to. So if I look at this carbon right here, that's an sp3 carbon. So the sp3 carbon has a 25% S and 75% P. The sp2 carbon hydrogen, that's the alkene, it has basically the hybridization of sp2, so that's a 33% S, 66% P. Comparing to the alkyne, you have basically sp, so that's 50% S, 50% P. What is that supposed to mean? As we mentioned previously, the more S character the carbon does have, the closer the shared electrons to that carbon nucleus, and that makes the hydrogen loosely attached, easier for the base to abstract. And that's the reason behind the pKa being lower for the alkyne hydrogen, comparing it to the alkene, comparing it to the alkane hydrogens. So that's important to keep in mind. So the pKa, as we mentioned, they are actually found in the pKa chart. So you don't really need to memorize those numbers, but it's very important that you keep in mind that alkyne hydrogen will always be much more acidic than alkene hydrogen or alkane hydrogens. And that's true when we have a terminal alkyne, because if we have an internal alkyne, there is no hydrogen to be abstracted. And that's important to keep in mind. And the example, as we mentioned previously, is this one. For example, if I look at the terminal alkyne, I have a hydrogen that has a pKa of 25. But if I have an alkyne that's an internal one, I don't have a hydrogen attached to either of the two. What do I have? I have an alkane hydrogens. These have a pKa of 50. So when we talk about acidity, we want to make sure that we have alkyne hydrogen in the first place to have basically the reaction with a base. But if I don't have a hydrogen to start with that's attached to an alkyne, then there is no base acid reaction. Usually, terminal alkynes, when they react with a base, they require the use of a strong base to deprotonate those hydrogens. And that, as an example of those strong bases, is an amide, NH2-. So whether you use lithium amide or potassium amide or sodium amide, it's totally fine, but you cannot be using hydroxides or alkoxides. They are not strong enough. And the justification is by looking at the acid-base reaction. So if I have an alkyne right here, has a pKa of 25, reacting with a sodium amide, that's going to give me basically the alkyne, which is the acetylide, to be more correct. So the acetylide anion with a countercation, that's sodium plus NH3. The pKa of the alkyne is 25. The pKa of the conjugate acid of that sodium amide is 36. And we learned in previous chapter that the acid-base reactions usually exist in equilibrium, and they favor the higher pKa side, the weaker acid. And imagine if I use a hydroxide. So the OH- is going to give me H2O, so pKa of 16. So I'm going from 25 to 16. That's not going to be a favorable equilibrium to go to the right. It's going to be actually more toward the left. So if I have a hydroxide or an alkoxide to be used as a base reacting with a terminal alkyne, it's one of the two scenarios. Either I'm going to get 50-50, 50% alkyne and 50% acetylide, or I may get much more alkyne rather than getting acetylides, as it is going to be not a strong base to be used to deprotonate an alkyne hydrogen. So that's important to keep in mind. Here's another example. So we have the cyclohexyl acetylene. That's the common name. If I want to name it IOPAC, it will be one cyclohexyl ethyne. One cyclohexyl ethyne. So this is reacting with sodium amide, so that will give you the sodium acetylide plus ammonia. As we mentioned, internal alkyne don't have hydrogen to be deprotonated. Therefore, if it reacts with a sodium amide is not going to deprotonate that alkane. It's going to be basically no reaction. Because think of it this way: pKa of an alkane is 50. pKa of the corresponding ammonia, if we assume it's going to react, that ammonia is going to be 36. The equilibrium will favor the reactant side. And that's why there's a huge gap between the two, that there will be no reaction to start. How do we generate the amide, sodium amide or lithium amide or potassium amide? Well, here's an example. So we have the ammonia to start with, plus sodium in presence of a catalyst, such as iron 3 plus, iron 3 chloride, or iron 3 bromide. That will be a source of iron 3 plus, and that's going to give me basically the sodium amide plus H2. So it's more of an acid-base reaction, so that will basically generate a stronger, much stronger base compared to the ammonia. And once we have that ready to react it with a terminal alkyne, that's when I will be able to generate the acetylide structure. Now, the acetylide ion, we learned in the nucleophilic substitution chapter that it is actually a strong nucleophile. So think of it as a C triple bond N. That's also a strong nucleophile. And the bulkiness of it, of the acetylide, it actually pushes it to go through SN2 when I react it with a methyl halide or a primary halide. So if I have a methyl halide or a primary halide, I will expect a nucleophilic substitution reacting an alkyne or acetylide anion with the RX. So here's an example. We could see the acetylide, once it's generated from the sodium amide and the corresponding alkyne, will give me that acetylide to react as an SN2 pathway to give you basically the extended alkyne. So we go from a 4-carbon chain to a 5-carbon chain. So that's an application where we could be using SN2 reactions of acetylides reacting with RX. Now, it's important to mention that we cannot have a secondary or a tertiary. Why that is? The bulkiness of the alkyne anion, which is the acetylide, will push the reaction to go through E2 rather than SN2. So here's an example. We have an isopropyl bromide. You would think it's not sterically hindered, but it's actually enough that the alkyne, the fact it's a bulky one, it will rather grab a hydrogen from the adjacent carbon to give you the alkene rather than the SN2 outcome. So we don't get an SN2 when we have a secondary or a tertiary halide reacting with acetylides. So that's important. So here's an example where we're asked actually to generate this alkyne from the acetylene. So we have basically an ethyl and we have hexyl. So we know that we're going to have to basically insert 2 alkyl groups. Doesn't matter which one you start with. So the first step will always be the sodium amide or the lithium amide or the potassium amide to generate the acetylide and then attack the alkyl halide. So in this case, the hexyl bromide was added first to give you the hexyl side, the hexyl carbon chain inserted, and then sodium amide the second time reacted, followed by an ethyl bromide will give you the desired structure. Now, it's important to keep in mind, we can't just throw in one step excess sodium amide followed by both alkyl halides to be thrown in at the same time. It doesn't work like that because, first of all, you're not going to be generating both anions. Second of all, you're not going to have a control over which one is going to be attacked first, if any. So that's important that we have to do it in terms of equivalency. So first equivalent of the base, followed by the first equivalent of the alkyl halide to insert into one side, and then do the same to insert on the second side. Those alkynes, once we generate the anion, they are actually strong nucleophiles that can react with a carbonyl carbon. So when they react with a carbonyl carbon, they will open up the pi bond to form a tetrahedral alkoxide. And that alkoxide, once it gets protonated, preferably using H3O+, will give you the alcohol. So it's going to be an acetylenic alcohol. So we could see it here clearly that if I have an alkyne reacting with sodium amide to give you the acetylide, it's going to react with an aldehyde or a ketone, and that will generate basically the propargyl alkoxide or the acetylenic alkoxide, which will generate, once we protonate with H3O+, I prefer not to use water. It has to be actually H3O+. That will give you basically the propargyl alcohol or the acetylenic alcohol. So whichever of the two terms you use, perfectly fine. So this is a nucleophilic addition reaction. This is not a nucleophilic substitution reaction. So reacting acetylide with Rx, where Rx is a methyl X or a primary X, that's an SN2 reaction. But if I have an acetylide reacting with a carbonyl carbon of an aldehyde or a ketone, that will be a nucleophilic addition because you are adding the nucleophile and you are generating an alcohol at the end. We are not substituting anything in here. Here's some examples. So we have the acetylide reacting with an aldehyde, and that will usually give me, once we protonate, a secondary alcohol. So keep in mind that we have to do 2 steps. The first step is going to be the carbonyl substrate, and the second step would be H3O+. Don't throw in H3O+ with the carbonyl in the same step. Why? Because you will be basically protonating that acetylide, and you're not going to have it react with the carbonyl carbon. So it's important that we insert the H3O+ as a second step. We could see it clearly here that starting with the alkyne, we deprotonate, we form the acetylide, reacts with benzaldehyde, that will attack the carbonyl carbon. So you end up basically making a C-triple bond CO- where the phenyl is attached. And step 3, H3O+ will generate the alcohol. So it's going to be always a secondary alcohol when you start with an aldehyde and an acetylide. But it will be a tertiary alcohol if you have the ketone instead. Here's an example. So we have an acetylide reacting with a carbonyl of a ketone that will end up opening that pi bond. So you're going to make an alkoxide again. And that alkoxide, once it's protonated, is going to give you a tertiary alcohol. You can see a real example here. Cyclohexanone reacting with acetylide. How do we generate this acetylide? Once again, sodium amide plus the corresponding alkyne, which is ethyne in this case, followed by H3O+. That will end up basically attacking this carbonyl carbon, and this O- becomes an OH. So that's a tertiary alcohol. Here's an example. It's a synthesis example. It's asking us basically to start with acetylene and show how we can make this acetylenic alcohol. So we know that the acetylene basically have to be deprotonated to generate the acetylide and then react with ethyl bromide or ethyl iodide, and that will end up making this 1, 2, 3, 4. So that's but1-ine. And once we make that but1-ine, we react with sodium amide to give you the acetylide that's ready to attack the aldehyde, the cyclopentane carbaldehyde. This aldehyde will go through nucleophilic addition with the acetylide, followed by H3O+ will give you the acetylenic alcohol. So it's important to keep in mind that we have to go through the SN2 Rx with the acetylide first, because if I react the acetylene with sodium amide to give you the acetylide, and then react it with the aldehyde, that's going to give me an alcohol. So if I have the alcohol side in first, not the ethyl, and I react the terminal alkyne, which has the alcohol already, with sodium amide, I'm going to have a competitive acidic hydrogen. The first acidic hydrogen is going to be the alcohol, has a pK of 16, and the second acidic hydrogen, that's the alkyne, that's pK of 25. So if I insert the alcohol first, I'm not going to end up able to insert the ethyl. So it's important that we do the SN2 first before the nucleophilic addition. That's a very important note to keep in mind. Every single time we have an acetylenic alcohol where I'm going to be in need of alkylating the acetylene group, I'm going to have to do that first, then do the nucleophilic addition. This is an example where you could see the order of the steps need to be actually followed properly so that we get the desired product at the end. Now, there is a synthesis way of an alkyne starting with an alkyl halide, but the alkyl halide has to be actually a geminal or vicinal. There's no preference. Both will go through the same process, that is E2 reaction. So the removal of 2 molecules of HX will be actually the outcome of this reaction. Now you have to have a very strong base to be used, and there is no preference to which one to use. Could be the KOH or could be the sodium amide. Now keep in mind, when we say vicinal dihalide, we're talking about basically two halide groups or two halide substituents sitting on two adjacent carbons. When I say geminal dihalide, we're talking about two halides sitting on the same carbon. And as I mentioned, there is no preference to which one to use to get to an alkyne. Now, keep in mind that the internal alkyne may be the favored product. If I have a competitive pathway to give me an internal versus a terminal, you may end up having the internal. So there is probably a better selectivity when we use a certain base, meaning KOH will favor the internal alkyne, NaNH2 will favor the terminal alkyne. The bulkier base size, which is in this case is going to be the nitrogen versus the oxygen, it makes actually the preference for the nitrogen base, containing base, to give you the terminal alkyne. And that's important to keep in mind. Now, the high temperature, we don't have to memorize these numbers because all what I need to write is actually sodium amide and heat, because some substrates you may actually have to go beyond 150, and some substrates you may have to not reach that temperature. So that's important to keep in mind. Now, in the case of terminal alkyne, you have to actually follow that heat and base step with water, so that will protonate the generated alkyne anion from the base medium. Once you react with water, that will be giving you basically the alkyne structure. So once again, it's an E2 pathway. So you generate the first alkene by having the first HX to be released. So the base will grab the hydrogen to make an alkene, kick off the second carbon, X. So you have an H from the first carbon and X from the second carbon. And that will give you basically the vinyl halide. Goes through the same process again, using a base and heat, will deprotonate that hydrogen and generate the alkyne once you kick off the second X. So that's important to keep in mind, that it's going to be a concerted mechanism, E2 pathway. No carbocation formation in this reaction. The same thing would happen if I would have a geminal dihalide. So the first hydrogen will be deprotonated, forms a double bond to kick off the first X. So you're forming a vinyl halide, just similar to the previous one. And the second molecule of base will grab a hydrogen from the vinyl halide to give you the alkyne at the end. So whether you form a terminal alkyne or a internal alkyne, there is no preference which base to use. Both will do the same job. But if I have a competitive pathway between forming an internal versus terminal, then I need to think of the sodium amide if I want the terminal alkyne to be formed, and I need to think of the KOH if I want the internal alkyne to be the structure. Here's an example of 2,3-dibromopentane. So it's a vicinal dihalide. So we could see clearly it's going to be an internal alkyne to be formed. So the first hydrogen will be deprotonated with KOH to give you the vinyl halide once it kicks off the second carbon Br. And then the second KOH will come in and do the same job of E2 reaction to give you at the end an internal alkyne. You're not going to be getting an alkene unit at the terminal and an alkene unit in the internal. You're not going to be forming a cumulene. That's not going to be the case whatsoever. You will be forming an internal alkyne as the major product. Now, the remaining yield, it could be basically a starting material that then go through the same process, as it is going to be it's an endothermic reaction. It requires a lot of heat to push the reaction forward. So the remaining yield, it could be just a starting material. And the next part, we will learn reactions of alkynes. We will see how similar they are actually to a lot of reactions that we've seen already in the alkene chapter.